So let's do a thought experiment here for a second. If we had just a scalar equation instead of a matrix vector equation, what would that look like? That would just be some number y. We can imagine taking just one data point here. Y is equal to x times m. So we would just have our scalar equation, and let's ignore the b for the moment. If we had this scalar version of this equation, so here's our scalar version of that equation, we could just solve for m by dividing. So we could divide both sides by x. X's cancel out here, and then we would have the value of m that we want. So this is what we would do with a scalar equation. You can't really divide by a matrix, that doesn't work. But what we did talk about briefly is the matrix inverse. So we can take a matrix inverse in some cases. If A in particular is a square matrix, and if it's invertible, which are conditions we're not going to talk about in this video, then we can take a matrix inverse, and then we could actually just multiply both sides of this equation by A inverse, and we would have our solution. So that would result in a system which looked like A inverse times y is equal to A inverse times A times m. And of course, as we said, A inverse times itself, A inverse times A is equal to the identity, and the identity times a matrix or vector is equal just to that vector or matrix, and so we just end up with m, a vector. And so if we could take the inverse of this matrix and do this algebra, then we would be able to directly solve for the values of m. And this would be a case where we had a unique solution. Now, because we, as we discussed before, we have scatter in our data points, we can't get a unique solution. We have no unique solution. We have to do something else. And so what is done is actually to try to find a solution, m, which minimizes the total residuals. So we said that before, we want to minimize the difference between the observed and predicted data. And so we can write this in a slightly different form. Same equation, slightly different form. So we want to have y minus a times m equal to 0. If that's the case, then we're fitting all the data perfectly. If that's not the case, then this is not going to be quite equal to 0, but we want it to be small. And so if we were to write this as, let's say, a summation over all the data, we could write this as a sum, I equals 1 to n, where n is the number of data, and then we would have y minus our prediction, which would be mx plus b. So there's our prediction with our m and our b parameters. We want that. This is going to be the residual, the difference between the observed and predicted data. So that will be Ri, the ith residual. And again, our least squares criteria, we're going to square that residual and then sum over all the residuals. So we want to minimize, we want to pick values of m and b such that this sum of all the residuals squared is as small as possible. And we can do this in our matrix vector form by saying y minus a times m. So there we are. And the equivalent in matrix vector form of the square is this transpose operation. So we can take the residual vector transpose times the residual vector, and that's essentially the residual vector squared and summed. And so this criteria now, we can try to minimize over m this quantity, where now m is our vector of unknowns, both m and b, and we try to solve for what m and b should be such that this quantity is minimized. We'll talk about how we do that practically in Python in another video. So just to wrap up this video, we've talked about matrices and vectors. We've talked about linear systems and solving linear systems. We want to use the least squares criteria, minimize the sum of the squared residuals to find the best fitting parameters for a given model. In this case, we've looked at a straight line model. We could look at other types of models like quadratic models or cosines and sines or whatever. In either case, the approach would be the same, to try to find the model that minimizes the misfit between the observed and predicted data.